Yeah, dear civil engineering people, today we will discuss about the transverse forces induced by draped tendons. Now, it's not that in pre-stressing beams, we are always providing tendons in a straight profile. You can change the profile of the tendon. For example, in this case, the profile of the tendon is having a kink at the center. This tendon is blue in color and it is having an eccentricity E at the center and E equal to 0 at the supports. In the second case, there is a parabolic cable which is being provided inside the simply supported beam, and we are applying the pre-stressing forces P. Now we will inquire how the pre-stressing force at the edge for kinked tendon as well as parabolic tendon is going to provide or react for the beam concerned. Now proceeding further, here we go. You can see that this is a simply supported beam which is having tendon with the kink in the center, and the kink is provided at the center, and the eccentricity values are 0 at the supports as well as at the center. The eccentricity value is E. Now the pre-stressing engineers can pre-stress at both the ends. They are providing a compressive force of P. So now we will just check what happens when the pre-stressing force is applied at the supports. Now here, this pre-stressing force is resolved into P cos theta and P sin theta. As you see, half of this beam is taken and represented here. This theta is very small because this theta is negligible. So you can see that if you take the sine component of the theta or tan component of the theta, that is equal to theta approximately, and because of this the P cos theta is approximately equal to P, and the P sin theta could be written as P multiplied by theta. Now you can see the explanations in the right hand side. Since theta is very small, theta is also equal to sin theta, that is equal to tan theta, which is equal to this E divided by L by 2. So you can see that this triangle has been taken here. The length of the beam, half of the beam is taken and length of the beam is L by 2, and if you put tan theta will be equal to E divided by L by 2. So you can see that the theta value is ultimately 2E by L, and cos theta is equal to 1 approximately, because theta is very small. Since theta is very small, it has these effects on the components which is being resolved into P cos theta as well as P sin theta. There is horizontal component and vertical component. Now you can see that this P cos theta P will provide a moment of P times the E. And what about the P sin theta? This P sin theta, you can see that for the simply supported beam at the supports you have two components, P sin theta and P sin theta. Now if you write down the equilibrium equations, these would be balanced by 2P sin theta here. Now this is here written as Fp equal to 2P sin theta, and we know that the theta is 2EA by L, substitute 2EA by L, and substituting all the values you get Fp equal to 4PE by L. So this is the ultimate resultant, that is in the form of 2P sin theta. This tendon provides a pre-stressing force of 4PE by L or 2P sin theta. This 2P sin theta is equal to 4PE by L. This is the pre-stressing force, or the opposite force which is being provided by the tendon at the kink. So if you provide kink for the tendon, it will create and ultimately a pre-stressing force of 4PE by L, which is acting upwards. So this beam is now efficient and enhanced when compared to the simply supported beam with the normal reinforcement. So in case of pre-stressing provided with the kink, it is going to provide you force in the opposite direction of the external loads, that is equal to 4PE by L. Now Now, if you want to draw the bending moment diagram due to the pre-compressive forces, you can see that P times P sine theta multiplied by, at the center it will be L by 2. So if you substitute all the values, P sine theta into L by 2 equal to P into sine theta is 2E by L multiplied by L by 2. Ultimately you have P. So definitely we have these two expressions, that is the force exerted at the center by the cable. This is the force provided by the cable with the kink, and bending moment due to pre-stress is nothing but P times E. As I told you earlier, the force is acting, pre-stressing force is acting at the supports, and the kink at the center is having eccentricity E. So P times E gives you the moment, and the cable is going to provide you enormous force, which is 4 times the pre-stressing force multiplied by eccentricity divided by length of the beam. Now in example 2. In example 2, the pre-stressed concrete beam with the parabolic profile is represented in the following figure. It is then subjected to forces, pre-stressing forces P at both the ends, which are applied at an angle theta, and we have to find out what is the upward transverse force exerted by the cable. Now this is the second case. In the first case we saw the pre-stressed concrete beam having kink. In the second we will realize that this cable is going to provide a transverse force in this way for the beam. So we will evaluate what is this transverse force, and we can call it as the FP, or in this case particularly we can call it as WP. So we will try to estimate what is the upward transverse force exerted by this cable, which is blue in color as represented here. Now here we go. So as I told you, the upward force WP is going to be calculated. Now it is also equal to FP, as I told you. Now this is a simple derivation where we already know that if the cable is having a profile of a parabola, the equation for the parabola is y equal to minus 4 into eccentricity divided by x by L minus x by L the whole square. In this, the horizontal direction is the x direction and the vertical direction is the y direction. So this y is a function of x. Here y is equal to function of x. Now previously from the fundamentals we know that the equation for this parabolic profile is y is equal to minus 4 times eccentricity multiplied by x by L minus x by L the whole square. Now, if you take the differentiation of this parabolic profile, ultimately you get dy by dx equal to minus 4e by L into 1 minus 2x by L. This represents the slope of the cable at any point along the span. So at any point along the span, if you want to know what is the slope or theta, you can definitely use this equation minus 4e by L into 1 minus 2x by L. Evaluating the above equation, if you want to find out what is the slope when x equal to 0 at this location, and what is the slope at x equal to L, that could be evaluated by using this equation dy by dx. On substitution of x equal to 0 or x equal to L, we finally end up with the two values, both are equal but opposite in sign, which is equal to 4EA by L. So here you can see that the value of theta is nothing but 4EA by L. Now, so this theta is obtained here. Now, if you want to know what is the curvature of the cable, so definitely we know that the curvature is related to bending moment, and d square y by dx square is equal to the curvature, which is called as kappa p here. So this mathematical notation is kappa p. Now this kappa p is equal to 8e by L square, which is obtained from this dy by dx. Okay. Now here E is the sag at the midspan, L is the span length of the beam, X is the horizontal coordinate measured from the left support. Note on that we are writing all the equations by measuring X from the left support. So X is in the towards right as represented and shown in the figure. Now we will try to find out what is the value of kappa p. Now this Kp, you can see that this cable, from this cable we take a unit length of the cable and we draw the free body diagram. So this diagram is free body diagram. So here you can see that the cable is exerting forces P at both the ends, and at the center you have Fp. We don't know what is the force Fp, so we have taken unit length. This Fp is nothing but Wp. Okay, so here if you draw a line at the center, the kappa p is divided into Kp by 2 and Kp by 2. This is kappa p by 2, kappa p by 2. Now here, as I told you, kappa p by 2 is the angle between the force upward force P, that is the pre-stressing force, and the horizontal line, that is the x-axis, and the downward pre-stressing force is also experiencing an angle of kappa p by 2. So this Fp equal to P times kappa p by 2. So here you can see that Fp equal to 2p sin Kp by 2. So how do you know it is 2p sin Kp by 2? Because if you resolve the component p vertically, here for this you will be getting here p into sin or tan kappa p by 2, which is equal to p into Kp by 2. So similarly for the other force P also you will get the value of P into kappa P by 2. So adding this you will get 2P into kappa P by 2. So that is equal to PKP. So here it is represented Fp equal to PKP, but already we know that this Kp is 80 by L square. So on substitution of this Kp, we get here P multiplied by Kp is equal to 8 times Pe by L square. So this is the force exerted by the cable on the beam. So this pre-stressing force applied to the cable at the anchorages will exert a force of Wp, which is equal to 8 times the pre-stressing force multiplied by eccentricity divided by the L square. So we can see that the final force exerted by the parabolic cable, which is pre-stressed, is the 8P by L square. Now here the upward force exerted by cable has been derived, and it is mentioned as 8 times Pe by L square. So you can see that as you change the parabolic, as you change the profile of the tendon from kinked to parabolic, you are getting the upward force, the huge upward force is being generated by the cable as we change the profile from the kinked to the parabola. So this parabolic profile has a lot of advantages, and it is being used in lot many bridges, bridge girders, and also in wherever it is required for residential buildings or the commercial buildings. When people go for precast pre-stressed beams, they most of the profile is provided as parabolic, because this parabolic profile will have a good effect and enhanced upward force which is going to be provided by this cable, and it will be efficient for increasing the capacity of the beam when compared with the RC beam. This pre-stressed concrete beam has a higher capacity because of the parabolic profile. So this is a great advantage of the parabolic profile of the cable, which is being embedded inside the concrete beam and which is going to exert an upward force that could be tolerated by the beam, and also the beam with an enhancement of the parabolic profile is efficient in resisting the external load, and the capacity gets increased. So you can see that 8 times the pre-stressing force multiplied by the eccentricity by L square is the force exerted by the cable. So thanks a lot for watching. If you have any doubts, you mention in the comment section, and subscribe the channel.